We now have enough information to talk about one of the central questions of machine learning, which is, what is learning? So what we have right now is we know that our data starts as this matrix of numbers, and we convert it into these features which characterize these qualitative aspects of the image. These features are then fed through a mathematical model, which spits out 0 or 1, which tells us if we have an apple or a banana. However, there was one crucial step in there. When we created that mathematical model, we had to choose parameter values. So let's go back over that. We have this function f of x, where we know its form is going to be the sigmoid. We chose the form such that it looks like this. And for a given w and b, we can plot this, and it will always look like a function which goes from 0 to 1, where what we want is that it's 0 whenever we have an apple, and we want it to be 1 whenever we have a banana. Now you can recall that when we change the value of b, what happens is we shift this line back and forth. And when we change this value of w, what we do is we make this line either steeper or shallower. And if we choose these values correctly, we can have this line such that it almost always gives a 0 when we have an apple, and a 1 when we have a banana, and this then will be our mathematical function that our computer tells us whether we have an image that's an apple or a banana, given our input data. However, we had to choose these values of w and b, but we can deconstruct exactly how we did this to be able to find out a computational algorithm for automatically generating these values. So what did we intuitively do to get this right? Well, if you look at this image, you probably see that these two apples are classified as a banana, because if you were to put their average amount of green into this function, it would spit out that a value that's very close to 1, which would say this must be a banana. So the way that we would fix this is we'd shift this line over by increasing b a little bit. And what's going on in our brains is we're saying, if we increase b a little bit, then we'll make the line a little less bad. Let's write that down. If we increase b, then the model is more correct. But notice I said the first time this same thing a little bit differently. I didn't say more correct, I said less incorrect. Right? Because we have a direct way of measuring how incorrect we are. So what does it mean to be incorrect? Well, it's incorrect if an apple is classified as a banana. But since we don't just have exactly 0 1s, we can interpret this number that's between 0 and 1 coming out of our mathematical model as a probability of our input being an apple or banana. So what we can do is we can take this distance right here as our bad distance. So we can say, we want our apples to be 0, and so the amount above 0 that the line is the amount of bad that we had in that prediction. Similarly, if we put a line up here at 1, all of our bananas should be at 1, and so this distance from 1 at every single banana point is our bad distance. So another name for this bad distance is the cost. So cost is really just a way of saying the amount that a prediction is incorrect. Now what we do with the cost is we want to add them together, right? A good model will have a small amount of total costs. So the cost function is going to be the sum of all of the different costs. So cost of x sub 1 over all of our data points. Now we don't just add up the cost, because notice that the distance here is the distance below 1, which is negative. The distance here is a distance above 0, which is positive. So we'll have directionality issues, and you can come up with weird cases where you'll sum to 0 just because they're canceling each other out. So what we want to do is we want to have our every single data cost only be positive, right? So that way it's 0 when it's perfect, but positive for any imperfection. Easy way to do that is just to square it, because any number squared is going to be positive. So this is what we know of as the sum squared error. And the sum squared error is a very nice cost function to work with, and it's a very common one to use. So if you take your distances between what the value should be and what the model says it is, and you sum the squares of all of those values, you get a cost which basically says how poorly your model's doing. And now what you want to do is you want to change your parameters such that your model does less poorly. And so we have this mathematical model here. And what we can do is we can perturb b just a little bit, right? What happens when we change b? We can calculate a new cost. And if that new cost is lower, that was a good change. If our new cost was higher, that was a bad change. Now notice that what we can do at this point is we can say, what is the derivative of the cost function with respect to b? That is what would happen if you did a very, very infinitesimal change, right? Instead of doing a big change, you just do a very small delta b change here. And when you do that itsy bitsy change, does the cost go up or down? That is calculated by this partial derivative, the change in c dependent on the change in b. Now, if the change in c is going down when we increase b, then that means that is going in the right direction, right? That means that our total badness in our prediction is going down when we increase b, which means that we want to keep on increasing b. And what this tells us is a simple algorithm to decrease the amount of error in our prediction is to calculate these derivatives and move in the direction that is negative of the derivative, because negative means that the cost function will be decreasing. This algorithm is called gradient descent. And this is actually what we did intuitively, right? So when you looked at this model and you said, well, I have these sliders, you probably bumped b a little bit and saw, hey, it made my predictions a little bit better. You probably bumped w a little bit and said, hey, it made my predictions a little bit better. You bumped b a little bit more and you say, whoa, now I've gone too far, it's making my predictions worse. So then you bump it back a little bit. That process of always bumping in the direction to decrease the cost or make your predictions better is exactly the gradient descent algorithm, where now we mathematize it by saying, what direction do we go in? Well, the direction that we go in is precisely the negative direction of this gradient. So if we increase b and c decreases, then that would give us a negative value, and we'd want to keep on doing that. And when we go too far, the sign of that will change, and we will no longer want to keep on increasing b. So the gradient descent algorithm is exactly what our intuition says we should be doing in order to make these parameters correct. And this process of finding the correct parameters automatically using these types of optimization algorithms is the learning process in machine learning.